First off, thanks a lot to everyone that is coming here to my talk called My Code is Faster Than Yours. Let me prove it to you. Let me first introduce myself a little bit. So my name is Francois Martin. I'm a senior full-stack software engineer working at Hurricane, and we develop software for customers. We also do some consulting, and we have offices in Basel and also Dortmund in Germany. And also I am an active member of the Swiss Testing Board, where I'm also a member of the Advanced Expert Level Working Group. And I'm also an author of the upcoming security test analyst syllabus. And also you may notice on the top right, there is a QR code. If you want to get the slides, you can scan the QR code at any point during the presentation. It'll be there in every slide, so you don't need to do it now, but you can, of course, if you like to. So yeah, So first, before we go into the performance of regular expressions, I'm curious to hear, who of you read the abstract of my talk? Wow, that's actually quite a lot. I would say like maybe 10, 15 people. That's quite nice. I wouldn't have expected so many of you to do that, because at least that's what I heard from other attendees so far, that usually people don't really read abstracts. But the ones of you that didn't read it, I really recommend you to have a look at it after the talk, because I think it's a very worthwhile read and it's based on a real story. You probably will feel it be a bit more familiar once you've heard this talk, I would say. So first of all, let me see. So put your hands up. Who of you used a regex before, or regular expressions? Okay, so that's practically every one of you. That's what I expected, kind of. So who of you liked using regular expressions? Put your hands up. Okay, so there are more than I would have expected. So maybe 10 people or so. So thanks for the bravery, for lifting your hands. And then I think it's also an important distinction. Who of you liked writing regex? Okay, so that's a lot less. So maybe 5 people or so. So yeah, that's really interesting to see. I kind of feel like that represents like what I experience at work. And let me show you an example of a regex that I found at work, which I needed to rework in a custom project a while ago. This is how it looked like. And I'm sure every one of you will be able to instantly tell me what this code does, right? Just by looking at it briefly. Instantly. Just as I was able to do, for sure. But of course, I'm just kidding. So just to make it a bit easier for you to understand what this does, let me give you an example, input and output. So essentially what it does is it strips some white space characters like tabs, and also removes some illegal characters, as the name implies. So like, for example, backslash, which is considered a illegal character in this case, and some other characters. And it produces a string like this. And I mentioned that I needed to rework this one. Let's say the main initiative for reworking it wasn't that it was a regex or that it was badly readable. The reason was actually that we needed to fix a redos vulnerability. So those of you who have used the regex before, or at least especially if you have written a regex before, and you don't know about redos, I really recommend you to look into this. It's like a denial of service attack, where you use a regular expression which overloads a service. And you can see on the bottom, there's like an example attack string. This method was used on customer-provided data, so it was untrusted data. So a customer could, for example, provide this data that is the attack string here. And by doing so, they would be able to generate a lot of load on the server, because it would occupy the server for a very long time evaluating this regex. And so I needed to rework it, and also we had some performance issues with our application. So it was also kind of a good opportunity to improve the performance here a bit. So here I was thinking how I would rework this. I mean, first option would be to just keep it a regex, but to rework it to make it not as susceptible to redos as it is currently now. This would have been an option, but of course this would be quite tricky. Oh, and by the way, you can see it is underlined, this redos here. So when you have the slides, when you scan the QR code, you can just click on this link and it will lead you to a documentation. And also have a lot of links scattered throughout the presentation. So feel free, if you're going through the presentation, to just click on the links if you want to learn a bit more about this. So yeah, and the other option was to just rewrite the code to not use a regex. And this is usually my preferred approach because I personally feel like it's more readable and usually it's also faster. And so I rewrote it, and this is what it came out with. And you see, I was also a bit surprised at the end how much code it truly was. I don't expect you to read all of it, just, you get a feeling it's quite a lot of code. And you can imagine once I submitted this for a pull request, then my colleague, he came up to me and he was like, "Are you sure we need to do it like this? Can't we keep it a regex and just fix the redos issue?" I tried to convince him that it was more readable, but he told me, I feel like the regex is more readable. I don't understand how he came to this conclusion, but yes, I can imagine it's kind of like a matter of taste, right? And so I had to pull another card to convince him. So my idea was to maybe bring in the angle of performance because, as I mentioned before, we were having some performance issues, and solving it with a regex without changing it over to this code would be a lot more difficult to fix this redos issue. So essentially I told him the performance of this one is better, and he didn't really believe me given that the code was so long. So I kind of had to prove it to him to be able to get this code through in the pull requests. So what I did was I used JMH, and then I have to say I was able to prove to him that the code was indeed faster. So let me show you what the results were. So this is like a graph that you could produce with the results you get from JMH. You can see the dark gray bar is the option that was with the regex that you've seen before. And the light gray bar is with the iteration approach, so the approach that I have rewritten it to. And you can see it's not even close. So you can see it's around 4 to 8 times faster, depending on the string that you use as input data. And by the way, the replacement character ratio, I'm not sure if you can read it, but on the very left, it says replacement character ratio. This essentially means how many of those so-called illegal characters you have per this many characters. So meaning if you have a low number, then this means that there are more illegal characters in the string. And if you have a high number, then there are less of them. And what I also find quite interesting is if you look at this, you will notice that if you have a length of 2000 characters in a string, then the 2 in front of it is the one where you have a lot of illegal characters. You can see, of course, as expected, as you have more things you need to replace, of course, the performance is worse than the one where you need to replace less characters. So this is kind of as we would expect it. But what I kind of found interesting was that the regex approach was also significantly slower the more replacements you had to make proportionally. So for example, you can see that if you compare the numbers for the iteration approach, you can see that the numbers are almost the same for each of the different. So for example, for 2000 length, no matter how many characters you need to place, it's a very small difference, around 20%. But if you look at the difference between the two regex approaches with a string that has a length of 2000 characters, then this is a lot more. And I also calculated this to be around 50%, so it's really significant. So there's another advantage to using this approach. Not only is it faster, but also with it being more consistent, it's another big advantage because this way we also have less security issues this way. So let's get into micro-benchmarking, which is kind of the topic of my talk. So first, let's start with a definition. So the HPC wiki, it says that micro-benchmarking is measuring the time or performance of a small or a very small building block of a real program, with emphasis being on real program here, because it's really important that you measure something in the real world, because else it's very difficult to tell if you are measuring correctly or not. You will see this a bit later, why this matters. And here it also says this can be a common data access pattern, a sequence of operations, or even just a single instruction. So it can be quite small, actually. So the state-of-the-art tool that you can use for this is JMH, which is short for Java Micro Benchmarking Harness. And this is kind of the state-of-the-art tool that you can use for Java or for other JVM languages like Kotlin and so on. So there are also other ways to micro-benchmark. Me as a full-stack software engineer, I also like to micro-benchmark sometimes in JavaScript. So here there are also other solutions. There are not many that great options, I would say. The big advantage is there are some web-based tools, but they are maybe not as statistically significant. I mean, you've seen, I also was able to include the margin of error that we had in the previous slide in the graph. But here, with the first two tools, you can't really have that. You can just have a basic number and get a rough feeling. But most of the time, this is probably good enough, I would say. And you can see I also linked here two examples that I made. One is of an approach where I compared different ways on how you can sort an array of integers. And also I made one where I compare a regular expression again, but in JavaScript this time. Not this exact scenario, but one similar to this. And then there's also a library called benchmark.js, which you could use. It's quite old. It's from 2016. And it's not maintained anymore, but it still is kind of, at least from what I could find, the best option that we have right now. I mean, let me know if you have any other knowledge about the tool that can do this, but to my knowledge, this is the best one, apart from the other two that you could use, especially if you want statistically significant results. And then one thing you have to keep in mind is also that micro-benchmarking is best suited for especially comparing the performance of different implementations under controlled conditions. So if you want to understand and improve the performance of your application in real-world scenarios or conditions, then you should do profiling instead, which is another technique this talk is not focused on. So let's start with setting up JMH, because I want to allow you, by the end of this talk, to be able to set up your own performance benchmark, just like I did. We are using a different example here. I will introduce it in a minute. But first off, I would recommend you to follow the README MD of the JMH repository really closely. And this is really just to make sure that you get the best accuracy possible. Because with micro-benchmarking, as we are measuring something that is so small, there are a lot of potentials to introduce some kind of error, and we really want to avoid that. So, for example, the recommended way is to use Maven and to generate it with this archetype. You could, in theory, use it with Gradle, but it's not the same, at least not guaranteed. So this is a command you can run to get a basic JMH project going. And you can see you can replace the group ID and the artifact ID with the ones that you have that you want to use. And then this creates a folder with the same name as the artifact ID that you specified here. And then you just open this folder into your IDE. And next we have to consider, what do we have to compare here? So who of you has seen something like this before?
No.
Okay, it's surprisingly not that many. So this is what we call an HTML encoded string. So sometimes if there are, let's say, slight bugs in a web application, it could be that you see something like this in the web browser. And this is something that you sometimes need to decode in order to be able to read it. And this happens sometimes if you have some encoding, decoding issues, or you're kind of having problems with, for example, not using UTF-8 or something consistently. And so decoded, it will look like this. So you can see it's a lot more readable. So yeah, recently I had to do this quite a lot of times, and I also had to do this with a lot of strings. So I knew there were a lot of different libraries out there for decoding, but I didn't know which one to pick, because First, what I of course did was to try and see if all of them fit my requirements. So I wrote a test case to see if all of them, decoded them properly as I expected them, because there could be, of course, some edge cases that maybe some of those libraries don't cover. And then I was kind of wondering which one is the fastest, especially in my case when decoding lots of different strings. Because as I mentioned, there wasn't just one that I had to do with every request or something, but it was a lot of them. And so optional, what I kind of recommend you to think about is, if it's possible, of course, is to think about what is the expected outcome of the measurement you are doing, and why is it the expected outcome. So in this example, it's kind of difficult because, you could look into the different implementations and make guesses on how the performance would be. But it's a lot more difficult. If you think back to the regex example we had earlier, there it was a lot easier in advance to make an assumption. Like, for example, I knew that regexes are rarely really optimized and rarely really fast. And this is why I knew already that my iteration approach would probably be faster, especially since I paid attention to not perform too many iterations and be able to do this with as few iterations as possible. But exactly, it usually makes sense, because then at the end you can compare with what you found in the beginning, and you can see if that matches it. And if it doesn't, then usually this means that you should maybe look into why this was the case. And also what is important, maybe you heard me mention the word, what is the fastest approach? And this is very important to keep in mind, that fastest is actually not always the same. This really depends on the context that you are considering. So it's really crucial to be able to make an accurate microbenchmark, that you know the context of the application really well. So usually you want to replicate the production conditions as closely as possible with a microbenchmark. And also, depending on the data that you use, the performance can vary significantly. So just to give you a simple example on how you could think about this. If you look at quicksort, for example, generally it operates with a complexity of O of n log n. And this is kind of, considered to be one of the fastest sorting algorithms for most cases. But however, depending on the implementation of the quicksort, of course, it could be that if you have sorted data, that the quicksort degrades to O of n squared in terms of the complexity. And then in this case, if you have a lot of sorted data, then other sorting algorithms are better used in this case. So for example, let's say you have a production application and you have a lot of almost sorted data and you're just doing some fine sorting, then probably it is not the best choice to use quicksort. And also, if you are microbenchmarking only on randomized ordered datasets, and in production you mostly have almost sorted datasets, then your result will be different, because, for example, the quicksort will perform much better than other sorts, while if you would choose a different sorting algorithm, it would maybe be better if you were doing a microbenchmark. So this could really lead you to a wrong decision, and this is why it's really important to be mindful of that. And ideally, you would use data you observed in production. You could, of course, anonymize it to a certain degree, but be sure that you anonymize it to a degree that doesn't change the performance. This is, of course, always a bit tricky, but ideally, or you could also monitor the data that is sent from your customers and so on, but this is usually the best approach. And also, for the best accuracy, it makes sense to also benchmark on your production hardware using the same JRE. Because depending on the processors, there may be some small differences in how the code could be executed, and this could lead to also different outcomes. Of course, at this point, you are probably testing something where the difference is quite marginal. If you have a big difference, then probably it usually doesn't make that much of a difference what kind of production hardware you're using or what JRE you are using. So the second step we need to do is we need to add a benchmark. So once you executed the command that I showed you in step 1, then you will have a basic mybenchmark.java, which looks something like this. And so what you want to do is each method or whatever you want to test. For example, here we want to test the different libraries or the different methods from the libraries to do the decoding of the HTML entities here. We would put into each of its own benchmark methods. So it's a method that is annotated with @benchmark, and you can name it whatever you want, but just keep in mind whatever you name it will be used in the output at the end. And you can put your codes there and you create a separate one for each method that you want to compare against, for example, in this case. So we can simply call the method, we want to benchmark, and we are done, right? We just put it like this, and yeah, that's surprisingly easy, right? Unfortunately not, as you could have guessed. The Java compiler is, in this case, unfortunately, too smart, and it removes the slice of code as it notices that this code is redundant, because it is a static method that gets called, and it does nothing else than to just simply return a string. So it is not used in any other way. It's not, returned. So Java sees this, the Java compiler, and it notices that it's not being used. So it simply removes this line. And when you execute the benchmark, it won't do anything. So you need to be really careful of those things. This is a process which is called dead code elimination. And here, if you click on this link, this will lead you to a repository of GMH where you can see a code example of how this affects benchmarks in, if you execute it. So you can see firsthand the effects of this. So then if you want to just perform one operation, what you can do to fix this problem is to simply return the result. Like here, you can see we just changed the return value to return string, and we return whatever we executed. And this way, we can avoid this problem of Java eliminating it, because since it needs to return it, Java notices, okay, this is relevant in some way. But the problem was, in my production use case, I wasn't just testing one string, but I was testing a lot of different strings. And maybe you remember I mentioned that you should usually try to keep conditions as close as possible to production. So if you, in production, iterate through an array, for example, and you go through a lot of strings, you should also do the same thing in a micro benchmark to keep it as consistent as possible. And also, by the way, you've seen with the dead code elimination, there can be some gotchas, and we will see a few more along the way. And you can see this is also one of the reasons why, for example, it's a lot easier to benchmark in JavaScript, since you have far less of those issues there. But in Java, of course, since we have the Java compiler, JVM, and the just-in-time compilation, this is something that leads to some unexpected things we need to keep in mind when creating a benchmark for it to be accurate. So if we need to return multiple results in a way, or for example, if you have a for loop or something like that, you can use a concept in JMH which is called a black hole. So how you use it is just by injecting the black hole pH, for example, in the parameters of your method, and then you can use pH.consume, and this way you can pass it something that you want to not get eliminated by the dead code elimination, and then this way this tricks the Java compiler to believe that it is being used. So this is a really neat trick you can use. However, you need to be very careful when using loops. I mentioned earlier, if your production use case uses loops, you should use them too, which is true. But you need to pay attention. The just-in-time compiler is very good at optimizing loops as well. So of course, if you have in your production use case a for loop where you iterate through it, to be the most realistic, you also want to have this optimization because you want to be able to see how this optimization affects the performance. But if, for example, you just want to test with different data, with a lot of different data, don't fall into the pitfall of just trying to loop in your performance benchmark, because then, of course, as I mentioned, you will have issues because the just-in-time compiler will do some optimizations which could ruin your results. So also here, again, if you get slides with the QR code, you can, for example, click on this test different data, and then you will see an approach that is recommended by JMH, with which you can do this if you want to test different data. So next, let's look at how we can benchmark with states. So maybe you've seen earlier, we were using a string array. And actually, one particular thing about micro benchmarks is that usually you execute them in multiple iterations. So you measure multiple times, not just once. This way you get the better accuracy because there could be some variations from run to run. And also this allows you to determine the error. Like if you notice, for example, the range is from here to here, then you know that if, for example, this is kind of the middle, then you have this range where the results could be in. And so what you need to pay attention to is if you have a state that you use like this, one problem that you could run into it is that in JVM, there is another optimization which is called constant folding, which even if you use a black hole, it just reuses the same result in each iteration because it notices, well, here you're using the same the same strings array that is referenced here, and you use the same string out of that. So you have the same string object essentially, and you use the same string object here in every iteration. So it does it in the first iteration, and in the following iterations, it simply replaces the entire code with whatever you had from the first iteration. And again, this will lead to inaccuracies in your test. So you really need to be careful about this. And also, so I would not suggest you to do this approach. What I would suggest you to do instead would be to benchmark with the @state annotation that you can find in JMH. And this is how it could look like. So here again, you can click on the link if you want to find out more about, for example, what the different scopes are that you need to use and so on. I won't go into that into too much detail. But what I think you should know is that you should put your state into one of those separate state annotation inner classes, for example. And then you can also here add it as a separate parameter in your benchmark. And then you can access it this way here. And then this way you avoid this constant folding issue that you could run into. And also the link, by the way, shows you some more advanced ways. Like, for example, if you want to set up complex data, or you want to do some things that you don't want to count towards the benchmark results, how you could do them, how you could set them up effectively. So I also recommend you to add some other annotations. Like, for example, it makes sense to specify the benchmark mode explicitly. There, I will show you the most common two benchmark modes that I use or that I've seen in other performance benchmarks. The other ones you can find from the link again. And you can see one of them is the benchmark mode, which is called mode throughput. With this one, it measures how many executions it can perform within a given time unit. So for example, how many times can it execute your method within 1 nanosecond, 1 second. You can configure this as well. And you need to be careful because if you select this mode, this is the only mode where the score that you see at the end is, in this case, if the score is higher, this means the score is better. Usually with the other modes, the score is always, if it's lower, it's better. So just pay attention that you don't run into this trap and maybe you think that the performance is actually bad when it's good, or the other way around. And also annotations, by the way, like this benchmark mode, they can be placed on both methods and on classes. So depending on, you could, for example, define that for every method in the class by defining it at the top of the class that you want to have a certain mode. But let's say for a specific method, you want to have a specific mode. You could also do this by annotating the method separately. And then another one is called average time. Here, you measure the average time that it takes to execute your code. And here, again, as I mentioned earlier, the lower the score is, the better, because the lower the average time is it takes to execute your code, the better it is, of course. And these are some other annotations I recommend you to use kind of as a starting point when you're writing in your benchmark. These are usually good values to start off with and then tweak once you have them in. And you can see here this output time unit device, which is the time unit, like, for example, in average time, it defines, for example, in how many, it shows you in the output how many nanoseconds it took to execute it. And also, for example, in the throughput mode, it will show you, for example, within 1 nanosecond, how many times it was able to execute your method. And what I recommend you is, regarding the warm-up and the measurement annotations, here, if you have an error that is quite high, then I recommend you to increase the amount of iterations. Just keep in mind, as you increase the iterations, the benchmark will run longer. So I would say usually, let's say a benchmark with those annotations takes something between 5 and 15 minutes. If you increase it to 100 or 1,000, depending on what code you're measuring and how many cases you're measuring, this could take hours even. So just keep this in mind, that you kind of make a balance between those things. But as if it's necessary, if your error is really that high and you notice it's not an issue that you have in your code, then you have to do it like this. Then if you have some long-running operations, like you're doing some I/O, for example, or you have some very complex computations, then it could make sense to increase the time of the iterations. So 1 second is usually quite a good value. It's usually enough. Usually you could even go lower. But, if you have something that runs longer, then this could be something you should increase. And by doing this, usually you should be fine. Of course, there are some finer differences that you could pay attention to. But these are, not as relevant as the other ones I've showed you so far. And when executing the benchmark, if you want the most accurate results, keep in mind the things I'm about to show you. You don't absolutely have to do them. It's just if you want to really have the best results, especially if the results are close, you should do those things. Like, for example, there is a feature in the processors that we use in our computers, like in our laptops and our PCs, where it, for example, does like the power saving mode, where it reduces the clock frequency of your processor to save some power. Or where it has like a turbo boost feature, where it temporarily boosts the clock of your processor to perform better. And of course, if you have those enabled, then the results could be slightly skewed, because it could be that, for example, one of the methods is executed with maybe some turbo boost, and then for another one, there is maybe not enough, maybe there's too much heat on your processor and it can't do the turbo boost anymore. So this is something you should keep in mind. So if possible, try to turn that off. And also I recommend you to restart your computer just to start fresh and not have too many things running. And close all other applications, background processes, browser, IDE. We should only ideally have a terminal open. And you can then run the following commands in the terminal window. So just run maven clean verify and java-jar target /benchmarks.jar. Another advantage is, I mentioned that you should try and test on production hardware, for example. The big advantage is you could, for example, on your local machine run maven clean verify. This is the part that isn't really critical in terms of those points I mentioned earlier, because the measurement really happens when you execute this java-jar command. You could then take this benchmarks.jar file and upload it to your server, and then execute it in your production server. And then this way you get even more accurate results this way, by just executing it this way, if you can, of course. So then once we ran this is what we get as the result. So you can see it, I would say it's kind of readable. You can see the different scores that we have, the error that it was measured, and it also shows you the modes and how many times the measurements were executed. And usually what I like to do is to visualize them. Of course, that is not mandatory, but usually I feel like this makes it a lot easier to handle the data or to interpret it in some way, which is also our next step. Now that we have this data, we have to make sense of it, of course. So here you can look at the results. So you can see it's quite impressive what difference there is between the different libraries. At least if I had made an expectation in advance, I would have said that I wouldn't have expected there to be as big of a difference. I thought the difference would be more similar. So if you consider, for example, Spring here is 27 times faster than JSoup is, which was kind of crazy for me to see. Of course, this doesn't mean that Spring does it better than JSoup. I'm sure JSoup doesn't do a lot of unnecessary iterations just for fun, right? I mean, probably JSoup and Apache Commons text, they could be not as optimized, but that would be surprising to me, especially for JSoup, considering it's used quite a lot. I think most likely they handle some edge cases that probably the other libraries like Unbescape and Spring don't handle, I would say. So also here, again, be careful, check if it fulfills your use cases. Don't just blindly trust that, better performance is always better. And then also one thing I really like at the end of each JMH run, it prints you this reminder here. And it tells you, that the numbers are just data. To gain usable insights, you need to follow up on why the numbers are the way they are. Maybe remember I mentioned earlier, you should consider in advance what you would expect the performance benchmark to do. And here, if you have a result, you should also check, does it match your expectation if you had any? And also, if it doesn't, check why this is the case. Or, for example, again here, if the performance difference between JSoup and Spring is so big, think about why could this be the case. Look into implementations, for example, since they're open source. Look at why this could be the case, and then you'll be able to figure it out eventually. And also it mentions some other things, but one other thing I would like to highlight is it mentions to ask for reviews from domain experts. This is also something I would, of course, recommend you doing, because especially if it's a performance benchmark that you're doing for something that's very critical, then it makes sense to do this for sure. And also here it mentions, do not assume the numbers tell you what you want them to tell. Again, with things like the optimizations that the JVM and the just-in-time compiler does, you need to really keep this in mind, because numbers could tell you a different story than what happens actually in production. And also, this doesn't mean that the method that you tested here is the best in every scenario. It's just the best in this specific context that you tested in. This is something you should also keep in mind, which is why you really, as I mentioned in the beginning, should be paying attention to make your micro benchmark as close as possible to your production use case. And also you should verify to ensure that the functions you use work correctly. Like, this doesn't replace running unit tests or anything like this. Of course, as I mentioned, with Spring being so much faster, test if the functionality doesn't only perform well, but also if it works correctly. And also one thing you need to keep in mind, if you run the benchmarks yourself, for example, that I have shown you today, you most likely will have a different result than I have, because every hardware is different. And you need to keep this in mind. And also, what I really recommend you is JMH. I would say the interesting thing about it is, if you look at the project by itself, it doesn't seem like it would have good documentation. But if you look at the samples, and samples are kind of structured like a tutorial. There are quite a lot of samples, so you don't need to look at all of them. But at least I would recommend you to start with the first one and then go through each one of those, if you want to create an even better micro benchmark. Because, of course, in this talk, I didn't have time to show you everything, but I would say the most important things I was able to get across. And here you can learn a lot more about other rare pitfalls or other things you need to keep in mind to be able to write a good micro benchmark. So then I also have a huge list of links which you can look at if you need more information, which you can look at. And then I'm already at the end of my presentation. So thanks to every one of you for coming. I'm really glad that there's so many people here. Scan this QR code. You will get an email with the slides, and also will get the links to all of the micro benchmarks I've shown you today with the full code, so you can run it yourself and look at how I did it. Also, what you get is you get the template, which is a template repository on GitHub, which you can simply with one click create your own repository from it if you have a GitHub account. And then you can already start writing your own performance benchmarks, which makes it even easier than running this Maven command and so on. I hope you like it and you get some benefits from it. Are there any questions? And so the question was, if I, for example, have this regex example that I showed in the beginning, and refactored it as I mentioned in the code base, and now, let's say, a year later, somebody comes along and feels like, this is really, unreadable. I'll write a regex for it. How can we make sure that nobody introduces something that breaks it? Like, is there a way to constantly monitor that, for example, if somebody was to change it back to regex, that and would show that this was a bad change that we shouldn't do? And here I would say the answer is a bit difficult. As you pointed out correctly, it's a bit difficult because as it depends on the different machines, especially if you're running on CI or something like that, depending on the machines, if you define let's say, absolute value, then of course this could be something that is difficult. What you could try in a case like this, where it's so obvious, you could try to just, of course, you would, for example, need to then include this benchmark in your project by itself. You could, for example, try to build some automation around it and try to detect if the differences between the with regex and the with iteration approach are at least, let's say, half or 4 times maybe. This could be maybe a good approach to go about this, but at least to my knowledge, there isn't something out there. What I kind of think is probably a better approach to do here is to, for example, write an ADR or architectural decision record, write this design decision down so you don't miss it, or, at least if you don't want to go this length, just write a comment in the repository. It's still, in the repository next to the code line. Don't write this as a regex, it performs badly. It's something like that as an idea. Any other questions? Okay, so the question was, is it really fair to compare those two approaches here, where we have the regex and the approach of the iteration? Because since there's a RDOS vulnerability that you could exploit, this would kind of make the comparison unfair. So to answer the first part of your question, it is still a fair comparison because I made sure in the way that I did the benchmark that I didn't selectively choose cases that would cause this RDOS to make it comparable between the different cases. Of course, I could have exploited this and, did do a case that would exploit this exact vulnerability, which of course would have shown that it is slower, but this was not my goal because we knew that the RDOS was there all along. And the second part was if it wasn't possible to get rid of the RDOS, but it's a lot more difficult. There are some runtimes you can use that specifically, try to avoid RDOS, but they aren't 100% perfect. You would probably get 99% of the way there, but I just felt like as this was unreadable in the first place and unmaintainable, of course, as well, I felt like it would be the best approach to rewrite this in code anyways. So I didn't really consider this because it would have added a lot more complexity to the build. And I wanted to kind of avoid this, or at least the trade-off wasn't worth it. Does that answer your question? Yeah, thank you so much for the question. Really good question, yeah. Any other questions? Okay, so thank you all for attending. It's really nice to see so many people showing up.